Hello and welcome to this first video in section 13.4. Here we're going to introduce partial derivatives. Okay, so here I have a picture of a surface just in the first octant there. The equation is z equals f of x, y, and what we're going to do here is look at a point on the surface. I'll call that point P, and I've included here, say in green, this would be the cutout of our surface with the plane x is equal to a. Okay, so if I fix x equal to a and look at the intersection of that plane with our surface, we'll just get this green trace curve here. Okay, and then likewise, if I intersect our surface with the plane y equals b, I'm just going to get this orange trace curve. Okay, so now imagine that you're standing at the point P and you want to say measure the steepness of this hillside if you move in the positive x direction. Okay, how could we go about doing that? Okay, well, that's equivalent to asking, right, what the slope of this purple tangent is, right, as we move in the positive x direction. So here's the idea, right? Again, along orange, y is constant. I'm just letting x vary now. So what I can do is look at just this cross section, right, where only x is changing, y is held fixed, and I can just use what I know from Calc 1 to measure the slope of this purple tangent. Okay, so let's do that, right? In Calc 1, what you would do is you say, all right, well, first I'm going to just choose a nearby point, and I'll say it is delta x units to the right of a, so this is a plus delta x, and then I'm going to consider this point on the curve over here. And then what I can do is just draw what we call the secant line between these 2 points, and then measure the slope of this secant. Okay, so now here at this point at A, the height for z would be what? Well, coming back here, right, P is the point on the surface, and the x coordinate is a and the y coordinate is b, and so the height for z would just be the result of plugging in a and b into our function. Okay, now for this point, okay, what we're doing again is just changing x. Y is, as we move along orange, y is always fixed to be b, right? So this would be f of a plus delta x, but y is still just b. Okay, so now what I can do is write down the difference quotient for this secant line. So this would be f of, so in other words, just the change here of the outputs, f of a plus delta x, comma b, minus f of ab, and then I'm going to divide that by the change in x, which is just, of course, this little gap right there. So now what do I want to do to get the purple slope? Well, of course, I want to take the limit of this thing as we let delta x approach 0. Okay, so this is going to give me the slope of this purple line. Okay, so I'm going to give this a special name. I'm going to call this del f del x evaluated at p. Okay, so this is just like your dy dx notation you see in Calc 1, except here we're going to use this script d, which is referred to as del here. It's a lowercase del, and it's used in describing derivatives like this because we have to now distinguish whether we want to say move in the x direction or the y direction. Okay, now we also call this thing the partial derivative with respect to x. Okay, so now let's go ahead and do this similar sort of thing for the y direction. Okay, so if I'm standing here at P, and let's say now I want to move in the direction of the positive y-axis, so move down this green sloping hillside, I want to know what the slope of this pink tangent is. Okay, so go ahead and bring up our y cross section, and then we of course can just do exactly the same thing that we did up above. So here I would just choose a neighbor point on our curve, and let's say this is now b plus delta y, because again, right, when we're on green, x is constant. X is always a. It's just now the y that changes as we move along the green curve. And so here, right, the output at P, the z height, in other words, is just f of a b. Then the height here would be f of a still, because x is constant. And then y would be b plus delta y. And then right here would be my little run, right, my delta y. So the slope of the line between these 2 points, P and this neighboring point, would be, well, f of a comma b plus delta y minus f of a b. And then I'm going to divide that by, well, the horizontal change, which is just delta y. So this is the secant slope, so just as above, we're going to take the limit of this thing as we let delta y approach 0. And then naturally we'll go ahead and call this thing the partial derivative of f with respect to y now, evaluated at p. Okay, del f del y at p is this limit of the difference quotient. Okay, now if I knew the function rule, right, f, I could go ahead and actually compute these. That's not really what I want to emphasize in this video. It's just more a conceptual development of what these things are. And really the big takeaway from all of this, right, just to summarize what we've just done here, is that del f del x, in other words the partial derivative of f with respect to x at p, is what? It's just the slope of our surface at the point P in the positive x direction. Or in other words, it would be the slope here of our orange sloping hill, right? Or equivalently the slope of this purple tangent. Likewise, partial f partial y at P would just be the slope of the surface at P in the positive y direction. Okay, so in the next video, we're going to go ahead and look at how to actually compute these things, not using difference quotients, but rather just using some things we already know from Calc 1. Okay, so that's a good place to stop.